Welcome back. This is week 12 of inverse methods in heat transfer. In the last video, you would have seen that we had done OR gate and AND gate using logistic regression. We also tried to do XOR gate using logistic regression, and of course, we saw that it failed because this is not linearly separable. So because it was not linearly separable, we could no longer do XOR gate. But what really happened when we tried to do XOR gate using logistic regression, especially gradient descent, is that the answer converged, but to wrong weights. Okay. So it's not as if it did not converge. Gradient descent did converge, but it converged to the wrong weights. Now recollect that XOR gate is one type of data for this diagonal and another type of data for this diagonal. So we all know that it's 0, 0 gives you 0, 0, 1 gives you 1, 1, 0 gives you 1, but 1, 1 gives you back 0. So this data is obviously not linearly separable. Now, that's why we introduce some intermediate layers here. Okay, so we need at least one single hidden layer. So we can introduce this hidden layer. Let's put 4 neurons here in the hidden layer just arbitrarily. Okay, so we put 4 hidden neurons arbitrarily, and we can have one output neuron in this extra layer. So now, if we create a fully connected network this way, we of course need a bias unit, and we can put this in a separate color. So let's call all these initial weights as W1. So W1 has size, as you can see, depending on how you wish to write it, as 4 cross 3 or 3 cross 4. Next, we have these 4. So for now, I am ignoring bias here. This is what you will see in the code that I am showing here. Why 4? We can use any number of neurons if you want. Okay, I have just chosen 4 just for convenience, but you can use any number of neurons because it's really speaking just some arbitrary interpretation of what is the intermediate calculation. So this, of course, is 4 weights. This gives you W1 has 12 unknowns, and W2 has another 4 unknowns. So we have a total of 16 unknowns here, all of which will be updated as W is W minus alpha del J del W. This, of course, is what requires backprop. Now recollect how we did the forward propagation through this network. The forward propagation was, suppose we call this layer as Z1, that is the linear activation here is Z1, and this was X. So then X multiplied by W1 gives us Z1. So that's a linear transformation, gives us Z1. Then you take G of Z1, which was typically, we can take a sigmoid here. So sigmoid of Z1 gives us the nonlinear activation. Now the outputs here are A1. Then you do W2, which is this set of weights, times A1 gives you Z, which is the output here. And then, of course, sigmoid of Z gives you Y hat, which you can call A if you wish as the output. Remember that the loss function here was the binary cross entropy loss function, minus Y ln Y hat, minus 1 minus Y ln 1 minus Y hat. The important thing was how we do backprop in order to determine these weights. Now, I am just copied and pasted exactly what I had shown you on week 10. So remember, this is all from week 10 of our notes. So I have written the same thing here. You do a forward prop as Z1 is W1 times X. and after that A1 is G of Z1. And similarly, Z2 is W2 times A1, and A2 is G of Z2 or sigmoid of Z2. The backprop here I had shown you in quite some detail in the previous week's videos. The important thing is the final summation that I had here, that the forward prop goes as Z is W times A in all sequential layers. So Z here will be W times this. Similarly, Z here will be W times this. But there is also a nonlinear step in between. G of Z gives you A. And similarly, G of this Z will give you the A. Of course, I showed a different example. We only have one output neuron here. Finally, when we want del J, del W, ij, we have to take error of the output, error of the Z of the output, multiplied by the activation of the input. Okay, remember this entire dance of taking E is W transpose delta when Z is the W times the same A. So you will see that E k minus 1 is W transpose times delta k. And this basically shifts around. I had explained this in week 10. So notice this W transpose wherever there is W. And finally, notice that delta is G prime times E. Recall that when I look at G prime of Z for G of Z being sigmoid, means that sigmoid of Z is basically sigmoid prime of Z is sigmoid of Z minus 1 minus sigmoid of Z. Once again, I had discussed this in our earlier videos. So what we are going to do is do a code walkthrough of exactly this network that I'm showing here, which is 2 neurons in the input, then 4 neurons in the middle layer, and 1 neuron in the output. So I will show a hard-coded case of XOR gate, and we can see whether it fares better than the logistic regression code. So let's go ahead and take a look at the code. So here is a simple neural network. This is once again the XOR gate, but the change here is I have sort of hard-coded this for the XOR gate. The logistic regression code was written far more elegantly. This one is written a little bit more inelegantly because of these intermediate layers. I have written this in some detail. You should be able to run this and look through this and see that it makes sense for you. I would highly encourage you to, those of you who have taken the course for credit, you will have access to the code through NPTEL/Swayam. So here is the simple data. 0, 0, 0, 1, 1, 0, same as before. Okay, I have written, this looks like the OR gate right now. So this is here, let's change it to the XOR gate. So once we run this, since we have included the bias units at the beginning, we can now look at X, same as before, except now your ground truth is 0, 1, 1, 0. Now, what this function does is it gives you a random number between 0 and 1. So I'm going to just step, and now you can see W1 is a 4 cross 3 matrix. Sorry, minus 1 and 1. It's not 0 and 1. You get minus 1 and 1. So you create a 4 cross 3 random matrix. You can see those Hammer strings. Some random values are given initially. Again, W2, these sizes we looked at in just at the beginning of this. So this is just some 4 random numbers, total of 16 unknowns. Okay. Now I have chosen 10,000 epochs, a large alpha. But the key portion of the code here is the backprop code. So what we will do is step in slowly into the backprop code. Now notice this is not a general code. This code was written specifically for the network used for the XOR problem. I simply do in the backprop code, I'm simply doing just one single stochastic gradient descent with stochastic gradient step with the backprop algorithm sitting there. Now notice this n equal to 4. This is the number of X data points. Obviously, this is hard coded for the XOR gate. If you want some other case, then you have to change this code. What I am doing now is sequentially stepping through every single data point. The first data point we will step through is the 1, 0, 0 data point, which simply says that the bias unit is 1, but x1 and x2 are simply 0. Next data point will be 1, 0, 1, which is bias unit is as usual 1. Then you are doing 0, 1, then 1, 0, then 1, 1. Okay, so we run through those 4. For each one, let's see what happens. Okay, so I now select the data from that particular row. So what you should see for X now is 1, 0, 0. Okay, so this is the data set. And of course, the ground truth here is, if you have 0, 0, the ground truth here is 0. Now notice the first layer. First layer is whatever arbitrary value of W1 we had chosen, it will just propagate that and see how well that works. Okay, so you run through that, you see Z1. Now, why are there 4 values here? Because there are 4 intermediate neurons. So for this one single data point, we now have all 4 neurons being updated. So minus 0.03, 0.70, 0.61, and minus 0.62. What do these mean? Nothing. This is simply what the intermediate calculations are. We can now calculate the non-linearities at the specific neurons. We have simply taken sigmoid of the corresponding neurons, and we are getting 0.49, 0.66, 0.65, and 0.34. Now, this, of course, is just the end of the first layer. What we want to do is what happens in the second layer, which is the output layer. So the output layer is, now you take W2 and multiply that by A1. Remember, A1 is the output of the hidden layer. I would request you to maybe draw the figure by hand and just check this out. I am not able to show both the figure as well as the code simultaneously, but you can draw a figure just so that you can understand a little bit better. All these 4 neurons in the intermediate layer are now pre-multiplied by W2, and you should get the output of the last layer. So you should get just a single neuron. Let's see if the sizes match. W2 is 1 cross 4. A1 is 4 cross 1. So 1 cross 4 multiplied by 4 cross 1 gives you a single 1 cross 1. And that's what you should get at this point. So Z is minus 0.3855 and Y hat is 0.4048. So once you see that Y here was 0, but Y hat, your prediction is 0.4048. So here is the error. The error is what you calculate and say, okay, error is Y minus Y hat. What happened to J, our cost function? Remember that the cost function is not what we backpropagate. We backpropagate del J del W. Okay, so therefore, remember del J del W for a sigmoid or del J del Z for a sigmoid with binary cross entropy simply gives you Y minus Y hat. Okay, so that is why we typically never really have the cost function written here. You can draw the cost function, you can plot the cost function, as I will show you one in the pin case later on. But all we are bothered about is simply this value E, and then we start our backprop. So remember, backprop starts as E goes as W transpose or W2 transpose delta. This corresponds to the backprop corresponding to this equation. This here is forward. Z is W2 times A1. So the delta A1 basically becomes W2 transpose multiplied by delta Z. So that's what you see here as E1 is W2 transpose delta. And then, of course, we start the next step. The error in A becomes, this term is just G prime. Remember, A1 is sigmoid of Z. So this is sigmoid multiplied by 1 minus sigmoid multiplied by E1. Okay. Now here is the update. I have multiplied by alpha also and just done the full update. But basically the del J del W term is this, which is error in the output multiplied by the input. Similarly, error in the output multiplied by the input, and you multiply that by alpha for learning rate and you simply update. This should be, there's a small trick here. This should be Y hat minus Y, but there is a negative here which gets cancelled, and this looks like W1 is W1 plus delta W1. Okay, so we can go and do these steps. So let's take each step. So you can see E1 now is a 4 cross 1 matrix, because that's the error in Z1, and this was error in, sorry, Z1 is delta 1, and E1 is the error in A1. Okay, so you can now see DW1 is a 4 cross 3 matrix, and we are updating 4 cross 3 matrix. and we just move forward. So you can also see what delta W2 is. It's the same size as W2, and we can update it. So if we come out, this is one step of backprop. Of course, if we continue, you do 10,000 steps of backprop, you get an entirely new set of W's, an entirely new set of W2s. Remember, original set of W's were between -1 and 1, and so were W2. You can see that clearly these values have been updated. They have been updated constantly by feedback to ensure that you are getting close to the actual Y. So the final W's, we can now run them and see how well they do against the actual data. So for each one of them, so for example, I take 100, the original Z. So Z for this arbitrary W looks like some random values here. You look at A, that also looks as some random values here. You calculate Z, this is really negative, which luckily gives us Y hat, which is really small. So Y was 0 there. Y, I have it here. Y was 0 there, but Y hat is also 0. So we can actually come here and see what the output is. So you can see it's given 0, approximately 1, and it is given 0.5, which is not so great. So we can run this whole code again. Let me just run this again, just to see what the update is. And now it has given 0, 1, 1, 0. So we saw, I mean, incidentally, this was not planned, that for some bad initialization, you might not always get a great match. I can always increase the number of epochs here and it will match well. But you can see that in general, if I even run this again, for a completely different set of weights. So each time these weights will be different. It's a nonlinear regression problem. You need not obtain the same weights each time. But you get the XOR gate at least repeated. So the first one is the ground truth 0, 1, 1, 0. Y hat is coming approximately equal to 0, 1, 1, 0. This was not the case when we used logistic regression. Now, will this work only for XOR gate and we have to use logistic for, let us say, OR gate? That is not true. We can even basically run an OR gate classification and that will work completely fine. Of course, it's going to be a different set of weights now, but even OR gate works. What about AND gate? So AND gate would be 0, 0, 0, 1. And if we run that, you can see 0, 0, 0, 1. This matches that well too. Now, the problem, of course, is whether it is AND gate, OR gate, XOR gate, or indeed a much more complicated classification problem. Here is basically just a 4 data point classification problem. Regardless of what problem you use, the neural network will tend to do a decent job provided you give enough hidden neurons. The problem, of course, is we don't know what these W1 and W2 mean. So that is the problem. That's the standard problem of interpretability. So the neural network works, but it is not interpretable. The key here in this code was doing this backprop that I showed you. So we wanted to do the backprop explicitly. In more complicated examples like the ones that I will show you next, when we do a physics-informed neural network case, you will see that that's a little bit more complicated. In fact, we will have to abstract out the details into the programming language that we are using. We cannot write these. This code will be sitting somewhere inside that. In fact, TensorFlow, PyTorch, or MATLAB, as we are using, all these sort of remove these away from the user so that you don't have to do this painful backpropagation code. Nonetheless, it's important for you to see what sits here. Notice in particular this term A1 times 1 minus A1. When you want large chains, as I had told you earlier, we tend to use ReLU rather than use sigmoid or tanh, because this term tends to get small as you use large deep networks. So better to use ReLU wherever possible. I'll explain why we don't tend to use ReLU for things like physics-informed neural networks in many cases in the next video. So I hope this was a little bit insightful for you to go through a backprop for a simple neural network for the XOR gate. I will see you in the next video with an actual example for physics-informed neural networks. Thank you.